Hello students, welcome to Target IES. In this video, I am going to continue with module number 12 related to trusses. Till module number 11, now we know how to analyze a truss, right? If a truss is given something like this and the load has been given, now you can easily find what are the axial forces being induced in individual members, right? Now you are perfect in this. You can analyze this using method of joints or method of section depending on the question, no issues. So basically now in the part 2, what are we trying to analyze? We are trying to analyze how much deflection is taking place. Whenever there is a load W being acted on the truss, obviously it will show some deflection, right? Now we are trying to calculate the deflection using strain energy method or unit load method. Okay, so what is the strain energy method? Let me explain you in short. Just give me a second, let me erase this. For example, if there is some body, need not be trusses, it can be any body, okay, and you are applying some load W, what will happen? It will be induced by some stresses. This body is experiencing some stresses because of this external load. These stresses will also result in some strain, right? When you are straining the body, some amount of energy is being stored by this body. That energy which has been stored because of the straining, we call it as strain energy. Okay, this strain energy might be because of the axial stresses, shear stresses and bending stresses. Okay, in trusses, as we have discussed the assumptions very clearly, second assumptions or third assumption, please go through your assumptions once. What did I say? The bending moment and the shear force are negligible in the trusses. Only axial forces are predominant, right? Therefore, the strain energy in the trusses is because of this axial stresses only. Okay, the axial force divided by cross-sectional area, what you will be getting? You will be getting axial stresses. And the strain energy in the trusses is because of this axial stresses only. If you are taking a beam, okay, or if you are taking a rigid frame, so we have seen some rigid frames in the chapter 1, right? We have seen how whether they are determinate or indeterminate. We will be analyzing the frames in latter parts, so no issues. We will discuss this in detail. But basically, in these beams or in this frame, the strain energy is mainly due to the bending stresses. Okay, here the bending moment is predominant, and the shear force, the stresses due to shear force and axial forces are very negligible. So in beams and rigid joint frames, the strain energy is because of the bending stresses only. Whereas in pin joint frames, the strain energy is due to direct stresses only. Direct stresses any axial stresses only, because your bending stress and also shear stress are negligible. I hope it is clear. Okay, you can go through the theory once. You will be having the hard copy, right? Just go through the theory once so that you will be perfect in it. Okay, now before analyzing the deflection using the strain energy method, first let us try to understand how much strain energy is being stored by the body when we are applying different types of loading. Okay, what are the different type of loading conditions available? There are 3 different types of loading conditions available. What are they? Gradually applied load, suddenly applied load and impact load. Okay, let me explain you in brief what are these 3 type of loading. I will explain you the difference. For example, if there is a weighing scale, you know what is weighing scale, right? On which you can see your weight. Okay, so if for example if you are keeping 5 kgs, okay, later you again increase 5 kgs, again you increase 5 kgs, again you increase 5 kgs till you get 50 kgs. Okay, for example you get 50 kgs. This type of loading in which you are gradually increasing the load, we call it as gradually applied loading. Okay, now instead of keeping these all 10 loads at once, for example if your weight is 50 kgs, okay, you go and stand on this weighing machine. Okay, so this is suddenly applied load. It has been, all this 50 kgs has been applied in a single time, right? So this type of loading we are calling it as sudden loading. So what is impact loading? Now you are standing here, just jump onto this scale. You are jumping directly onto this scale. What will happen? That will be called as impact loading. Okay, so basically in gradually loading, the weighing scale, how was weighing scale? It was 5, then 10, then 15, it goes up to 50. In sudden load, all of the sudden, for the first time itself, it shows 50. In impact load, as soon as you jump, what will be the loading? It will be 50 or greater than 50. I think you would have observed this, right? I am sure you would have observed it would be greater than 50. The reading will first show greater than 50 and then slowly with time it will come down to the 50. Agreed? As soon as you jump, obviously the amount of reading, you might have seen this experiment, right? I'm 100% sure you have done this experiment in your life for sure. So when you jump on this, obviously your weight will be seen some like 80 kg or some 70 kg, and then all of the sudden within some seconds it will come down to 50 kg, okay, which is your normal weight, right? Agreed? So these are three types of loading condition. Let me erase this. Just give me a second. Let me erase this properly. Now let us try to calculate what is the strain energy due to gradually applied load. In the case 2 we will see sudden load, and in the case 3 we will see impact load. Okay, at least I hope you know this from the SOM concept. If there is load W acting on a body, what will happen to this body? This body will try to elongate. Agree? And what will be this elongation? Delta L? Delta L will be equals to WL by AE, right? Or PL by AE if it was P in place of W. I hope at least you remember or had this formula somewhere. Delta L is equals to WL by AE. See, this elongation is nothing but the deflection, right, in this case. Okay, so your deflection, if there is some load hanging like this, what it will be? WL by AE. Agreed? So that's the same diagram which I have drawn here. In the gradually applied load, how will be the deflection increasing with respect to the load? For the first case, I am giving 10 kg, 5 kg, and then I am increasing it to 10 kg and then 15 kg, and I gradually go up to 50 kg, right? In the example which I have given previously. So my delta is increasing with my W value. If I am increasing the W value, my delta is increasing. If I am increasing my delta W value, my delta will keep on increasing, right? So I will be getting a triangle. Agreed? If I am drawing a graph between load and the deflection curve, this curve will be called as load deflection curve because it is a graph between load and deflection. Okay, so what is happening? As the load is increasing, my deflection keeps on increasing, right? Therefore I am getting a triangular curve. Agreed? Whereas in suddenly applied load, your W value is constant. All of the sudden you are keeping 50 kgs, so you will be getting a straight line and you will be getting a rectangle. The graph of load versus deflection in suddenly applied curve, suddenly applied load is a rectangle, whereas in a gradually applied load it is a triangle. Remember, I hope you are very clear why we got rectangle in this case and triangle in this case, right? Now let us see the theory associated with this. So basically the strain energy which is stored in this body is nothing but the area of this curve. Okay, the area of this load versus deflection curve will be giving you a strain energy. Okay, so this note is very important. This can be asked as objective also. The strain energy stored in the strain energy stored is the area under the load deformation curve up to proportionality limit. Remember this. He might ask up to dash, up to elastic limit, proportionality limit, okay, yield limit, whatever. The answer is up to proportionality limit. Okay, the strain energy stored is the area under load deformation curve up to proportionality limit, and strain energy is always positive. Remember this one also. Strain energy can never be negative, it can be only positive. Okay, so what I have said, strain energy is nothing but the area of the load versus deflection curve. This load versus deflection curve is a triangle. So what is the area of triangle? Of base into height. What was base? Base was your deflection and height was your load. So delta into W divided by 2. What was your delta? Delta value here. What is the formula which you are going to use? WL by AE, right? Just substitute. WL by AE into W. What you will be getting? W square L by 2AE. This is your strain energy stored because of this load W. Okay, agreed? So this term AE, always remember this is called as axial rigidity. Okay, when the body is being experienced to the axial load, something like this, axial rigidity will come in place. Okay, if the body is being subjected to bending, in place of AE, what you will be getting? You will be getting EI. I hope you have at least heard this term, right? What is EI? Flexural rigidity. AE is axial rigidity because axial force is being acted. EI is flexural rigidity because bending moment. Bending is also called as flexure. Therefore, it is called as flexural rigidity. I hope it is clear, right? See, in this term I have L here. If I send L in denominator, what will it be? AE by L, right? AE by L is called as axial stiffness. Actually, in this chapter there is no much importance of axial stiffness, but as the chapters progress, I will be teaching you matrix methods. In matrix methods, AE by L plays a very important role. Okay, the stiffness plays very important role. Now let me erase. Just give me a second. Let's get back to our concept. Let us calculate what is the strain energy stored in the gradually applied load because of the gradually applied load. So we got strain energy stored because of the gradually applied load is nothing but W square L by 2AE, right? W square L by 2AE. Okay. Now let us modify this formula. This is the answer. This is the answer which we want. But let us modify it. So what is the stress? The stress is load by area. Agreed? So what will be sigma square? Load square by area square. I am substituting that in the equation number 1. Okay. What is the strain energy which I got? W square L by 2AE, right? So this one, you can see WL square by 2AE. So what I am doing here is I am multiplying it by A and dividing it by A. So what I will be getting? I will be getting W square L into A divided by 2A square by E. Now I can take it as sigma square, right? W square by A square, it is nothing but sigma square. So I can write my strain energy as sigma square AL by 2E. Area into length is nothing but volume, na? Area into length is nothing but volume. Just substitute V in terms of AL. What you will be getting? Your strain energy is sigma square V by 2E. Okay. You can write it sigma square or you can write F square also, up to you. It is up to you. Stress. Sigma represents the stress. So your strain energy is sigma square V by 2E. So this is the final result which you have got. Okay. What will be the strain energy per unit volume? So this is the strain energy of the body, right? Entire body. What will be the strain energy stored per unit volume of that body? So it is nothing but your strain energy divided by your volume. It will be sigma square by 2E. Okay. So this is about the strain energy stored because of the gradually applied. Now let us continue with strain energy due to sudden applied load. This is very simple concept and this is just the extension of gradually applied load. By now you understood to get the strain energy what we have to do. We have to draw the graph between load versus deflection, right? And the area of this graph will be giving us the strain energy stored in that member due to the applied load. Okay, very simple, right? So here in the suddenly applied load, we are applying all the W at the same time, right? So I am getting the straight line and the deflection is also constant, right? So I will be getting another straight line. So what did I got? I got a perfect rectangle. Okay, the area of this rectangle will be giving me the strain energy stored because of the suddenly applied load. But there is something which you have to understand. At the instant, as soon as you apply W, the deflection due to the suddenly applied load will be more than that of the gradually applied load. This is common sense, right? See, you are gradually applying load, but here all of the sudden you are applying load, so the deflection will be little more, right? How much more deflection will be there? It will be twice that of the gradually applied load. Okay, let me explain you what is happening. Please try to concentrate because this concept won't be taught in any coaching center or any university. Okay, now let us try to understand what is happening. As soon as you apply all the W at once, this body will elongate more. Okay, this body will elongate more. So what will be the elongation? Elongation will be 2WL by AE. That is twice that of the gradually applied load. Okay, so the strain energy stored will also be high, right? So what is happening to this high strain energy which is stored because of the sudden loading? There will be vibrations. Okay, this is I am talking about instantaneous time. This will happen in fractions of seconds. So what is happening? There will be vibrations. So when this body is releasing the vibrations, it is releasing the energy which is stored as the strain energy. So what will happen after some time? After some instant of time, this deflection will come back to WL by AE. Okay, agreed? So actually on the long run, after some time, if you give ample amount of time for body to settle to that load, your gradual deflection will be equals to the sudden deflection. Okay, but at the instant of loading, your deflection the sudden deflection will be twice that of the gradual loading. Very important bit which you have to understand. Okay, in exam if he asks what is the deformation due to suddenly applied load, you have to write it will be twice that of the gradually applied load. Okay, similar to the deformation, the stresses due to suddenly applied load will be twice that of the gradually applied load. Okay, as soon as you apply the load at that instant of time. Okay, I'm talking about at that instant of time where you are when you are applying all the load at once. Done. So let us draw this strain energy. Let us derive the strain energy. It is nothing but the area of load deflection curve. So by now you are perfect in this. No need to calculate again. Load into deflection. Load into, here the deflection was 2WL by AE. So I will be getting 2W square L by AE. Agreed? So very similar to previous thing. What I am doing, I am multiplying it by A and dividing it by A, so that I can get strain energy per unit volume. Okay, so what will be my strain energy? It will be 2W square L into A divided by A square E. So I can take it as sigma square, right? Again I can write W by A whole square as sigma square. So I will be getting 2 sigma square V by E. So this is my strain energy due to suddenly applied load. What will be your strain energy because of strain energy per unit volume? Because of the suddenly applied load, it will be 2 sigma square by E. Okay, agreed? Very simple. So very important bit which you have to understand. What was the strain energy due to gradually applied load? It was sigma square V by 2E. What is your strain energy because of the suddenly applied load? It is 2 sigma square V by E. So how many times is the strain energy because of the suddenly applied load more than that of the gradually applied load? It is 4 times. If you multiply your gradual strain energy due to the gradual loading by 4, you will be getting that of the suddenly applied load. Agreed? Very important bit. Give it 10 star because it has been asked in ESE, GATE, state PSCs, PSUs, almost all examination. Strain energy due to suddenly applied load is 4 times that of the gradually applied load. Okay, so this is the note which I have already explained. Please go through it once. When the load is applied suddenly, the bar vibrates, and after some vibrations are stopped, it will behave as a gradually applied load. So that is, after vibrations are stopped, your deflection will go back to PL by AE or WL by AE. If you are taking load as W, it will be WL by AE. Okay, again your stress will be P by A instead of 2P by A or 2W by A. Okay, so I said your stress value in the suddenly applied load will also be double, that is 2W by A, right? So it will go back to again W by A. Okay, so this is about strain energy stored in the strain energy stored due to suddenly applied load. Okay, so this is the note which I have given, not that important, so ignore it. So this is nothing but the strain energy in terms of stress due to the suddenly applied load. Okay, I told the stress due to suddenly applied load was 2W by A, right? Instead of writing sigma, you can write it in sigma dash square also. So it will be similar to that of the strain energy due to the gradually applied load. What was the gradually applied load? Sigma square V by 2E. Okay, very similar to that, the strain energy applied, the strain energy obtained due to the suddenly applied load in terms of sigma dash will be sigma dash square V by 2E. Okay, but sigma dash value is 2W by A. Okay, you will be getting the same answers. So not that important. Only important is 4 times that of the gradually applied load, which you should never forget. Now coming to the impact loading. Okay, now let us calculate the strain energy due to impact loading. Very simple thing. See, the sudden loading, if you lift, in the previous case we have taken W as a sudden load, right? Now lift the W and drop it. You will be getting the impact loading. Okay, so if you have lifted the W by height H, okay, and you drop it, if this was the original position of the bar, what will happen? Now the bar will try to compress, right? Now it will come back to this. Now it will go to this position, something like this. Agreed? So this deflection, let that be delta. Okay, so here let me tell you the formula clearly. The stress developed due to the impact loading will be W by A into 1 plus under root 1 plus 2 E A H by WL. Give this 3 star because this is not asked in exams. Okay, this is asked directly as objective. I'm not talking about ESC or gate. I'm talking about state PSCs or PSUs. Okay, you open any state PSC examination, whether it is of Andhra Pradesh, Karnataka, Bihar, it doesn't matter. You will find the stress due to impact loading is the answer. You have to select the answer. You will play with signs. In one option it will be 1 plus, in other option it will be 1 minus, like that. Okay, so the option is, the right answer is W by A into 1 plus under root 1 plus 2EAH by WL. Always never forget this, W by A into 1 plus under root 1 plus 2EAH by WL. Never forget it. Okay, basically the strain energy due to impact loading we don't calculate much, but it is very simple. So there is nothing here. The W is constant, the load W is constant. You are not increasing it or decreasing it. And what is the deflection? The total deflection will be height plus delta. Okay, so the height plus delta you have to take. The area will be giving you the strain energy. That's it. Okay, but the most important thing in this is this formula, the sigma, because of the impact loading. Okay, what if the H is 0 in this case? What if your height is 0? You are just keeping the load on it. It is similar to that of the suddenly applied load, right? Let us see what will be happening. This term will be 0. If H is 0, this 2EAH by WL term is 0. Okay, so what is left? Sigma is equal to W by A. Agreed? W by A into 1 plus root 1, which is 2, right? Root 1 is 1, so 1 plus 1 is 2. So your sigma is nothing but 2W by A. Okay, so if H is equal to 0, impact loading will become suddenly applied load. Your sigma will be 2W by A. Done? So simple. So I hope you learned something in this module. Now let us solve two small problems and end this module. Okay, see, very simple question. Strain energy stored in the member CD. Where is your member CD? This is your member CD. Okay, what is the axial force developed because of this load 10 kilonewton? What is the axial force developed in this member? So it is nothing but, if you apply sigma y is equals to 0, you will be getting FCD is nothing but 10 kilonewton only, right? Agree? Very simple. So now let us use our formula. What was strain energy formula? W square L by 2A. So what is the axial force developed? 10 kilonewton. Just substitute that, you will be getting your answer. So W square L by 2AE. Let me substitute W square. I got 10 kilonewton, right? 10 into 10, which will be 100 into length. Length is given as 2 meters. So into 2 meters divided by 2 into area. Just give me a second. Yeah, into Young's modulus. Okay, 2 to cancel. I will be getting my strain energy stored as 100 divided by AE. That's it. Very simple. There is nothing in this question. Now calculate what is the strain energy stored in the structure. So he is asking to find strain energy stored in the structure. See, if we want to know what is the strain energy in the particular member, what we have done, we have found the axial forces, and my strain energy was my axial force W square L by 2AE, right? Very similar to that. If I want the energy stored in the entire structure, you have to find the axial forces in all the members and you have to do the summation. Your strain energy will be sigma W square L by 2AE. That's it. That's it. You will be getting your answer. Now let us see this question. We have done a very similar thing, right? He is asking to find what is the total strain energy stored in this structure. So you have to calculate what are the axial forces in all the members first of all. So see, we have done a very similar question. Okay, but at this end I have 3 joints. So I am not interested in that joint. But let me go from this joint this time. Okay. So if you see this joint properly, what is there? If I apply sigma x is equals to 0, I know this member is a zero force member. Agreed? So once I know zero force member, I can ignore this member, right? Now it is similar to 2 members meeting with no external load. So this is 0, this is 0. Simple. So this was 10 kilonewton. So I got compressive force like this. So again, two members are meeting collinearly and a third member is coming and no external load. So again this is a zero force member. Okay, so this continues just like the above terms and all these members will get 0. Agreed? Very similar, very simple, right? So if this is a 0 term, again there are 2 members meeting and no external load because external load is 0. So 0 0. Again, two members are meeting which are collinear. Okay, so which are collinear. So third member is 0. Again, as there is 0 force, these two members are again 0 force members. Okay, and if you apply sigma x is equals to 0 at this bottom hinge, what you will be getting? You will be getting 0 again. Okay, so there are only three members in which the axial forces are being induced. Okay, so we have to summate all these three things and you will be getting your answer. So sigma p square L by 2ae is, or w square L by 2ae, it is up to you, p or w, it doesn't matter. So that is your strain energy. So you just have to write 10 is the answer, right? So 10 square L by 2ae plus 10 square L by 2ae plus 10 square L by 2ae plus 0, 0, 0, 0, 0. Okay, so you'll be getting 300 by ae as your answer. So simple, right? So why 10? Because these two forces are collinear. Yeah, as these two forces are collinear, this, to make sigma y is equals to 0, this should also be equals to 10 kilonewton. Very similar, this should also be 10 kilonewton because at this joint again sigma y is equals to 0, because at this joint again sigma y is equals to 0, so 10 kilonewton, 10 kilonewton. So all you have to do is summate the axial forces into length divided by 2ae and you will be getting your strain energy. Okay, axial force square into length by 2ae and you will be getting your strain energy. That's it. So in the next module we will be studying Castiglione's theorem. Okay, if you are perfect so far, no one is going to stop you. So Castiglione's theorem are quite important for objective purpose, so please concentrate in the next module. It will be very interesting and almost the theory will be finishing in the next module. Okay, so have a nice day. See you in the next module.